Hi, it's Robin. After that COBOL episode, I felt like doing something easy and relaxing like some assembly language programming. So I was reading through this excellent book, Programming the Commodore 64, The Definitive Guide by Raeto Collin West. An awesome book if you can get a copy. And by the way, it is available on archive.org to download as well. And here on page 268 is this neat little program that adds $ commands to add hexadecimal support to BASIC. For example, POKE D020, 1 works correctly. There's a relatively short BASIC program here to type in. I've already done that. Here it is. This is what we call a machine language loader. This is the decimal representation of the machine language program here in these data statements. And line 100 reads and pokes them into memory, and then sys828 starts it. So if we just run that, nothing seems to happen, but we can now poke D020. If we poke it with 0, changes the border color, and we can poke D021, change the background color. It even works in programs, so we could poke D020, 1 and then run it, and it changes the border inside a program. So this is an example of extending BASIC, and it's actually a bit easier than you might think. Oh yeah, and we can also use it if you just go with the print statement. You can then type in a hex value, and it will print it back to you in decimal. It's the common 53280 that we usually poke. However, there's a lot of times that you might want to poke an 8-bit value into memory, like FF hex, and it messes those kind of values up. It's actually interpreting it as FF00, or something like 80 hex. Again, it interprets it as 8000. So that's a bit of a flaw with this program. And also the book doesn't really show the full source code. It just shows a couple snippets of this. And I was interested in how it works. So let's go ahead and load up Turbo Macro Pro. Oh, and you can do 8-bit values, but you have to enter them as 16-bit values, like so. Just to make that clear, you can use it for the parameter of a poke, for example, but you have to type in all 4 digits of the hex. Okay, let's start Turbo Macro Pro, and we'll load in. Okay, so I've gone through and I've already disassembled that program, and as I was figuring out how it worked, I put in my own comments. So we'll go through that here. In the description below, there's a link to the D64 file, so if you want to play around with this yourself. So we're going to assemble to 33C. That is the cassette buffer, and it's a pretty popular place for small machine language programs to live, if you're not using cassette, of course. So I've kept it the same just to match the program listing from the book. And now these are just a couple labels of routines that are used. CHRGET, that's character get, character got, and eval. And I'll explain those as we go. So the first part of the program I've labeled setup. I just made up these labels. And this is to point the eval vector to the new routine. So here in another excellent book, Mapping the Commodore 64, here's the routine that eval AE83 convert a single numeric term from ASCII text to a floating point number. And it says here, this routine is vectored through RAM at location hex 30A. If we look here at 30A, yeah, this is a vector, which is just a 16-bit address that points to another routine. And Commodore BASIC has a number of these that were deliberately put here so that Commodore BASIC could be easily expanded. And that's exactly what we're doing today. There are actually several ways of expanding Commodore BASIC, but this is what's appropriate for adding the hex values. And so this will serve as a good example of one way of going about expanding the basic, the function of the basic. So all we're doing is loading the low byte of our new routine called eval hex, evaluate hex, and storing that in the vector, both the low byte and the high byte, and then returning. So when we type sys828, all it does is very simply installs our new routine into memory. It's that simple. Of course, what isn't so simple is actually writing the new evaluation routine. And that's what we're going to be doing next here. Okay, so here it is, eval hex. So the first thing we're going to do is tell BASIC that this is numeric data, not string. So we're just going to load a 0 and put that in 0 page location D, which is part of the BASIC system. This lets BASIC know whether it's currently evaluating a string, if it has the value FF in this location, or if it's numeric, if it's 0. So to be sure, we're going to put a 0 in there, that this is a numeric value, even though it's starting with a $sign. Okay, the next step is we're going to look for the leading $sign. So we're going to call this routine CHRGET, which we defined up here as 73. And this is a very short routine that's actually in 0 page. So again, in mapping the C64, there's this get next basic text character. Character get is a crucial routine which BASIC uses to read text characters such as the text of the basic program which is being interpreted is placed on 0 page to make the routine run faster. And here's a disassembly of the routine. So I don't think we have to get deep into that, but basically it fetches the next character of either the basic program or the buffer if you're in immediate mode, the line buffer that's at 200 hex. So we get the character and we compare. Is it a $sign? This is how we're intercepting the hex values. If it's equal, then we're going to branch to isHex, that's down here. But if it's not equal, we're just going to fetch the character again, which also resets some processor flags. That's why it's done a second time. For example, carry is clear if it's a numeric value, but if it's a string value, carry is set. And then we're going to jump back into the normal evaluate routine, continue normally. Okay, and then we're done. So we're only continuing on with our extension if the first character of the term is a $sign. Then here we're going to load X with 2, and this is, we're going to be processing 2 bytes, that's 4 nibbles. So we're going to just set the X register to 2, so that's a counter. And then there's going to be a loop here. And first we're going to get the very first character of the hex address. So again, jump to subroutine to character get, and we're going to check if it is an @ symbol. Now I'm in the C64 Programmer's Reference Guide, Appendix C, the ASCII and character codes, and that character get routine returns the ASCII value. The @ symbol is character 64, and the numbers are below it. The digits 9 down to 0 are below it. And then right after the @ symbol is the ABC and, of course, DEF on the next page of the hex values. Branch if carry clear is the same as branch if less than. So we do the comparison with the @ symbol. Branch if carry clear is the same as branch if less than when we're doing an unsigned comparison. And if it's clear, then that's to say it's less than, so we're going to assume the next digits are 0 through 9. This extension has very poor error checking actually. You could type in a whole bunch of other ASCII values and it would try to operate on them as if the value was 0 through 9. I'm not going to fix that today. So if it's 0 through 9, now if it's not less than, it must be greater than or equal to, and carry will be set. So we're going to add 8 to the value, but since carry's already set, we're actually adding 9 to the PETSCII value. And so the low nibble is now going to be A through F if the character was an A through F. This is converting from PETSCII into an actual hex value from 0 through F. So I realized I need to explain this better. So here I've made a little table with the character that is being received in the hexadecimal string from 0 through F. And here is the PETSCII value that is returned from the get character routine. So in decimal, 48 through 57 for characters 0 through 9. And the hexadecimal representation is what's important here, because we're trying to convert from this character into a hexadecimal nibble. So if you notice, the low nibble of characters 0 through 9 match the value that we want, 0 through 9. And we can just ignore the high nibble because we're going to be throwing that away in a moment anyway. So basically nothing needs to be done to convert from PETSCII 0 through 9 to hexadecimal 0 through 9, except throwing out that high nibble, which we will be doing in a moment. The only bit that needs a little bit of work is for A through F. Here's the decimal representation of those PETSCII values, and here's the hex value, 41. You notice that for A, the low nibble is 1, going up to F is 6. So to get that up into the range we want this low nibble to be A. So if we add 9, 41 hex plus 9 is equal to 4A. And that's true for all these. If we add 9 to all of them, 6 plus 9 is 15 decimal, and that's F in hex. Okay, so we're going to be adding 9, but in the code, we're only adding 8, and that's because carry is set. It's going to be 8. The add with carry automatically includes carry, and that happens to be set because of the comparison we just did. Carry is clear if it's less than, and it's set, that is equal to 1, if it is greater than or equal to. So that's why we're going to just add 8 plus carry, a total of 9, and that converts from this hex value to the actual hex value we want. And now the low nibble in the accumulator is the same as the hexadecimal digit that we are converting. So the conversion's done just with that little bit of code. Okay, continuing on. We don't care about the high nibble at this point because now we're going to shift that low nibble up to the high nibble. And we do that with 4 arithmetic shift lefts, which moves the low nibble, multiplies it by 16 by 10 hex, and shifts everything up 1 place in the hexadecimal number. So now it's shifted up to the high, and we're going to temporarily store it in 0 page location FE. Now we're going to deal with the second digit. Again, we're going to get the character, and again, check the @ symbol. This is exactly the same as above. If it's 0 through 9, the low nibble already equals 0 through 9, just because of PETSCII characters are laid out in memory. I don't know if that was a happy coincidence or what. And again, we'll add 8 plus the carry, and so the low nibble will equal 0 through F, matching the character. This is a bit of an optimization, a little bit of a hacky way of doing it, but it works. But it's not all that clear just to read it. Okay, and if not, we just skip over that if we didn't need to add it. Now we're going to mask off that high nibble. See, the 0, when you do a logical AND, the 0 turns all bits off, and the F allows all bits through. And then we're going to OR it together with the high nibble, and now we have interpreted 2 PETSCII characters and combined them into 1 byte of the same value. And then push it on the stack, decrement X, which is our counter, And if it hasn't been reduced to 0, from 2 to 1 to 0, then we're going to do that whole last step again. We're just going to loop once again and get another 2 digits. And now all we have to do is take that conversion and return it to BASIC. So the reason we stick it on the stack is it's just a simple place. When we're doing a loop, we know we can store it on the stack, and we don't need to use any other index or anything like that. Suppose it would be possible to store it somewhere else in memory and use X as an index. But anyway, again, I didn't write this. I am just disassembling what Raeto Collin West did many years ago. So now we're going to pull back the value from the stack, which is the low byte, the last 2 characters of the 4-digit hexadecimal value. And we're going to transfer it to Y. I'm actually not sure why he did this. I think this might be a vestigial remains from an earlier version of the program, pulling it from A, transferring it to Y, because maybe originally he was using a basic routine that expected a 16-bit value in AMY. But as it turns out, he just sticks in Y, pulls it again, and then he just stores AMY into the floating point accumulator. So anyway, I think it only costs us a byte, but I think that's a small misstep. I've certainly done that kind of thing even in my I've certainly wasted a byte or 2 in some of the programs I've shown in earlier episodes. Okay, and then we're storing this new 16-bit value in the floating point accumulator. And I think we've gotten into this before, that Commodore BASIC has very poor, almost non-existent integer support. Really, it expects all its values in floating point. It's got a 32-bit floating point system, so 4 bytes dedicated to the mantissa and 1 byte to the exponent. I'll get into that. I think I'll have to do another episode to get deeply into floating point sometime. But essentially, it's just storing the 16-bit value in there, and then setting the exponent. I believe this is 2 to the power of 16, because it's putting a 16-bit value in, but the floating point accumulator is actually a 32-bit. It's just a software accumulator. The CPU doesn't support floating point directly. And then 80 hex is an exponent of 0. Actually, it's reserved just for the value 0. Then 81 should be 2 to the power of 1, and so on up to 2 to the 16. What's happening next, which is to call this basic routine, basic ROM routine, BC49, which converts the 16-bit integer that we just stuck in the floating point accumulator, and it converts into the float that BASIC expects. Sorry if that's not the best explanation of that. We should probably look at that deeper in the future. That could be its own episode. And then finally, we're going to get the next character here, but we're going to jump to CHRGET, which has the effect of readying the next character and returning to whatever called this routine in the first place, so BASIC can continue normally. And that's it. We're done. So back arrow 3, and instead of pressing start, back arrow 1, and it'll quit out to BASIC here. And now we can do the sys828, and just to make sure it really is working, print that, whatever, right? 1111. I think that's right. And then sys32768 to go back into the assembler. Okay, so from that version, I went ahead and made this hex 7. These are just the different versions of my code. And I improved it so it would handle 2-digit hex values as well. And so I tried to do this in a fairly minimal, without rewriting everything. So the program is the same up to this point here. Okay, this is where my changes started. So it's about 1 screen of changes to do this. There's probably so many ways you could do this, and maybe some of you will think of a better way, and that'd be great. I encourage that. I'll make it clear that by making these videos, I'm not saying I'm the best at this. I'm just excited about it, and I'm hoping to pass on some of what I know to you. So the way I went about trying to solve this is that we need to check the third digit of the hex value. So if, for example, if we check the third value, and is that 0 through 9 or A through F? If so, we're going to assume it is a four-digit hex value like before. But if it's anything else, like, it could be a plus sign or a colon, whatever, then we're just going to look for 2 digits and assume that the first 2 digits are 00. We'll still be passing a 16-bit value on, but the high byte will be 0. So how to do that? We have to look at CHRGOT. So here we are again in mapping the C64. So I think this is kind of like a misprint here. That CHRGOT should actually be over in this column. But anyway, so this uses self-modifying code to get the next character. It's actually a 16-bit address here in memory. And you can see here increment text pointer, and then it deals with the high byte if necessary. So this is the location in memory. It's at 7A and 7B. It points to the current text that we're evaluating. So we need to load this address, which is actually CHRGOT +1. This is the CHRGOT here, is the load. And then the second byte is CHRGOT +1 and CHRGOT +2. So that's exactly what we're doing. We're loading CHRGOT +1, and we're going to store it in our own self-modification routine, also +1. And again for the second byte. And we're storing in here self-mod. This is what we call self-modifying code. This is a very simple example of it, but you're actually changing these operands. I usually put an FFFF to remind myself that that's what's happening. And because CHRGOT is still pointing at the $, so we're going to add an index of 3 to check the third character. So the $, if this was the Petsky representation, it isn't, I'm just using it as an example, then we're going to add 1, 2, 3 to look at that character. Okay, and then we're going to compare it with the Petsky for 0. If it's less than 0, that means it's an invalid character, and therefore we're going to branch to this 1-byte routine, which will push a 0 onto the stack here to represent that high byte, and it's also going to decrement x from 2 to 1 so that we only execute this loop once. So any invalid characters, any non-hexadecimal characters, not 0 through 9 or A through F, will go through this routine 1 byte. Okay, then we're going to compare with the colon. Okay, so if it's less than 0, that's any of these characters, we're going to only process 1 byte. And if it is this colon, if it's less than that, then that means it's going to be from 9 down to 0. Well, then that's a valid byte. So we are going to branch to just jump right into the loop and do 2 bytes worth. Okay, and then we're going to check if it's A. And if it's less than that, then it must be one of these characters here, which is also invalid. So again, we're going to branch to 1 byte because we just want 1 byte. And then finally, we're going to check for the character G. And if it's less than that, then it must be one of these hex letters, A through F, which is valid. So we're going to go a loop. If we end up here in 1 byte, then that means the third character is not 0 through 9 or A through F. So we're going to assume that we're just going to use a 2-digit hex value. Okay, just a quick extra note here. I released this video early for my patrons, and CS Bruce, who is a regular commenter on my videos, if you check the comment section, rightly pointed out that all this is not necessary, these 4 lines here, because what we can do instead is get rid of that self-mod and just point this to CHRGOT +1, like so, and then delete all these lines and simply use indirect indexed addressing to check the character. I got so hung up on that self-modification, I never even thought that it is in 0 page, so this is an option here. Usually when I'm using self-modifying code, it's not on 0 page, so this doesn't apply. So anyway, that's a big savings there. Thank you very much to CS Bruce. And that'll be saved as file hex 8 on the D64 that you can download below. Alright, and all the rest of the program's the same, except I couldn't help myself, and I did get rid of that little Y. Now we're just pulling it, storing it in 63, the low byte, and pulling it and storing the high byte in 62. Yeah, that floating point accumulator actually does go from high value down to low, contrary to most 6502 addresses where we do low byte and high byte. But it really doesn't matter when it's just this sort of a software register. You can do it however you like. Okay, so let's assemble that. Back arrow 3, and then back arrow 1, sys 828. Okay, let's try that with, did we break that? No, that still works. And that works. How about single 0? Oh, that works too. That might not be reliable though. How about 20? That should say 32. Yep. And just as a little example, here's a short basic program that makes use of these hex values. We're going to set V to D1000, which is the video chip address. Poke V plus hex 15, comma hex FF. And that enables all the sprites. And that feels a little more intuitive than poking 255, although of course after years decimal values feel just as natural too. But okay, we're going to poke a sprite on the screen at location 80, which is 128 hex. And this is kind of neat. We can do a little while loop here, which goes from 0 to FF, and then we're going to poke that into the sprite's Y position, and then next. And just because, let's try go to 40 to do that all again. All right, let's run that program. And there is our sprite moving through hex values, at least as far as our basic program looks. So poke D020, comma 0F. There we go, light gray. Thanks to my patrons who support this channel. If you're interested in being a patron, then please check out the link in the description below. There's some benefits like having your name in the credits and some exclusive videos too. Also, if you haven't subscribed, please do. All right, thanks for watching, and we'll talk to you next time.